Hello everyone, my name is Omar Boufous, and today I'll be presenting our work on centralized and distributed multi-region traffic flow control. First of all, why are we interested in this topic? Well, nowadays, as you may know, there are several problems related to traffic in urban areas, whether we're talking about the accidents that occur each year, with over 1 million people dying and 50 million injured, or other things you may have experienced yourself, such as traffic jams that waste billions of hours each year. But besides these time delays or the increased accident risk, there are other equally serious consequences, namely pollution because of carbon dioxide emissions and a higher fuel or energy consumption. This is a direct result of traffic congestion that basically every single major city is facing. And in our study, we are using perimeter flow control. That seems to be an efficient and sustainable way to improve traffic flow and mitigate the issues we just mentioned. This will be the structure of the presentation. I'll start off by introducing the concept of macroscopic fundamental diagram that we'll be using to model the dynamics of the network. Then I'll briefly present how we formulated the problem before explaining the perimeter control method we implemented to limit the incoming flow towards the network, and the optimization approach we used to not only perform perimeter control but also handle the routing inside the network. We will talk afterwards about the different distributed strategies we propose, and finally we'll have a look at the results we obtained and conclude on the performance of the different controllers. This work is based on the MFD, which basically gives the relationship between vehicle flow and density. And what it says is simply that vehicle flow in a given urban region is a function of the number of vehicles in it. And in our case, we use an approximation of the MFD, which is the piecewise function that can be seen on the right hand side. And this function has a particular shape, and what we can see is that the more vehicles we have in a given region, the higher will be the throughput until it reaches a maximum, and from there, when the region gets too populated, the outflow will decrease and tend to zero, which means that we reached a gridlock level and the maximum capacity of that region. In urban networks, we've got very heterogeneous areas, and one single MFD cannot describe properly the behavior of the whole network. That's why they can be represented by multiple homogeneous regions, and by doing so, we can study a group of connected regions, each one of them characterized by its own MFD. This is the type of network we are working with. We've got N regions representing areas. It could be a city center, for example, and all of them are connected to the outer region. This means they communicate and can exchange vehicles with that external area. And we define the set of regions that send vehicles to region I and those that can receive vehicles from region I. And Qij is the transfer flow from region I to region J. We can now write the evolution of the accumulation of vehicles in each region. And to get the next state, we just add what came in, the inflow, and subtract what went out, and that's the outflow. And since we will first be looking at perimeter control, we isolate the incoming flow from the outside, Q0i, and that's our control variable. Then we just define a new state variable x representing the deviation from the target values. Now, before thinking about doing perimeter control, we first look at if there are any conditions for it, because if we visualize the set of connected regions as one single system, one necessary but not sufficient condition of stability is to make sure that on average the total amount of vehicles that come in, so the inflow, is smaller than the outflow, which is the total number of vehicles that leave the network. It turns out that in our case, the inflow, which is the sum on the left, can be controlled, and that's what we're trying to do. This way we can keep the system in an overall stable state, assuming the routing inside the network between the regions is random. Now, this is a very intuitive way of looking at it, and we tried to come up with a controller that does this job based on Lyapunov stability theory. Using a suitable energy function V, we derived a boundary controller that limits the incoming traffic from the outside for each one of the regions of the network. But even with this controller, there are some cases where we lose stability and don't have a negative delta V anymore. This is not a surprise because we know that perimeter control is just the first step, and it's not sufficient, as we mentioned earlier, especially since the intertransfers are not controlled but rather random. And that's why we can end up sometimes with a region that is already congested, with a total inflow greater than the outflow, resulting in a state that diverges. So this method handles only the way the network communicates with the outside, but it says nothing about the way regions communicate with their neighbors. And this is the objective of this optimization-based approach, which is to not only control the incoming traffic, but also the intertransfers between regions. We use for this purpose the cost function J and formulate a convex constrained optimization problem that consists in minimizing the deviation, or we can call it the error x. Now this is quite straightforward and it works pretty well, as we will see in the simulations, but the total number of control variables is n squared, so depending on the size of the network, that can be a lot and involve heavy computations. But another more important problem is the communications overhead, because with this method we certainly control and optimize the state of the whole network in a centralized fashion. But for that, we need to know all the time the state of each region and what's happening everywhere in the network. So the question is, how can we do this differently, or can we actually do it differently and obtain similar or maybe even better results? Well, we already have a centralized perimeter controller that regulates the total coming flow from the outside, but the routing is random, so it's not optimal. And what we're doing here with the distributed policy is optimize locally the state of each region by controlling and redistributing its outflow sort of independently from the perimeter control by accounting for the traffic information in its surroundings. The first way of doing so is to just redirect traffic in a naive way towards all the neighboring regions. This way, each region shares a portion of its traffic with its neighbors. So in red, we see that region I receives a portion of the outflow of all its neighbors. The second way of optimizing locally the state of the region is to first assess the state of its neighbors and then decide to send vehicles only to the regions that are less populated. So all regions that are more densely populated than region I will send the same amount of vehicles to region I and other less congested neighbors. Here it's the same idea in red, except that we only consider regions J that are more densely populated than region I. Finally, the last algorithm will make sure that the traffic is redirected in a way that takes into account how much a region is congested with respect to I. This way, region I receives vehicles for more populated neighbors proportionally to how underpopulated region I is. And since we don't know the state of region 0, the external area, as part of the design of this third algorithm, we have to specify for each region a parameter that determines the proportion of traffic that will be sent to the outside. This is the controller that we'll be using for the simulations, as it's the most effective one. It leads to the highest convergence speed, which is not surprising given how it is designed compared to the first two. This is the network we use for the simulations. We've got 3 regions that have very similar characteristics, so very similar behavior as well. And the optimal accumulation point is at around 500. The first simulation, or the first figure, is the one for the centralized perimeter controller. The gridlock levels are the dotted lines, and the target values are depicted with the dashed lines. We can barely see them here. We'll see them more clearly in the next figure. We've got small fluctuations, but the system is brought back to equilibrium. And this simulation shows a case where the centralized perimeter controller works well, but this is not always the case, as we explained earlier. Sometimes, because of the randomness of the transfers inside the network, the states diverge and they cannot be brought back to equilibrium. The figure on the right hand side shows this distributed controller used alone. And if you remember, we proposed different strategies, and this one is the third one. Here we set the incoming traffic from the outside to a fixed value. As you can see, there are a lot of oscillations, but we're pretty close to the optimal operating point. Now, if we combine these two, this is what we get, which is way better and even better than the optimization based controller depicted on the right hand side. We've got a smooth trajectory and a convergence towards the target values. As a conclusion, we can say that the distributed strategy helps spread the traffic density in a nice and even way, although it's quite tricky to tune and adjust the parameters of the distributed algorithm. It's important to use it with the centralized perimeter controller. This way we have an architecture with two levels of control, because when they are used simultaneously, they achieve very good results in a simple manner without having to find the minimum of a global cost function. We converge rapidly and end up with a stable system with no steady state error or oscillations. Future work will include a more extensive study of the controllability of the system, along with a study of the regions of attraction covering the whole state space. And another direction of work would be to consider another type of network, and by that I mean a new topology, because as you may have noticed, our network is composed of regions that are all connected to the outside, and that's not always the case in the real urban networks. So a network with regions inside that cannot be controlled directly would be much more realistic. Another important aspect that's worth looking at is the quality of service constraints involving, for example, the average network travel time and delay, or the network queue dynamics. With this, I would like to thank you for your attention and suggest referring to the paper for further details. And do not hesitate to contact any of the authors for further questions.